Hello everyone, this is Neha Durvasla, a graduate student and Department of CISE at University of Florida. Welcome to my project presentation titled Narrowband Interference Suppression in Direct Sequence Spread Spectrum System using Adaptive Filters. This is for EEL6509, that is Wireless Communication course. The advisor is Dr. Dapeng Wu. Let me extend my thanks and regards to Professor Wu for advising and guiding me all through the semester. So let us now get on with the project presentation. So about the project, on this we present a very novel interference suppression method by adaptive filters in a direct sequence spread spectrum signal. The project can be regarded in two phases. The first phase spreads and spreads the signal without considering the interference. In the second phase, interference signal is added to the spread signal along with channel noise and is suppressed using least mean square and recursive least square adaptive filters. The performance is later compared, and we have some conclusions drawn from them. So initially, let's start with what the spread spectrum is all about. The idea behind spread spectrum is to use greater bandwidth than the required message bandwidth, but the power remains the same. The band spread is accomplished by using a code which is independent of the data, and a synchronized reception with the code at the receiver is used for despreading and data recovery. Spread spectrum, why is it used? It is used because it makes jamming and interception harder. A spread spectrum is of two types. It can be a frequency hopping spread spectrum. It can also be a direct sequence spread spectrum. So basically, a frequency hopping spread spectrum broadcasts the signal over seemingly random series of frequencies, while a direct sequence spread spectrum is in which each bit is represented by multiple bits and transmitted signal. So here we have a diagram. The black and white thing is a narrowband signal level. You can see the spectrum is narrow, whereas the noise level is random and the power levels of noise are very short. So figure 1 is narrowband signal, relatively easy to jam and intercept. So what we do here in spread spectrum is you spread the signal over the frequencies. As the pulses in time get shorter, the frequency bandwidth gets longer. So the signal is hidden under the noise. Now it's very difficult to jam or to intercept it. So that's the advantage of spread spectrum. So figure 2 shows the spread signal, the red one. As we move on, this is a direct sequence spread spectrum. Each bit here is presented by multiple bits using a spreading code. A spreading code spreads signal across a wider frequency band, which is proportional to number of bits used. And usually, a 10-bit spreading code spreads signal across 10 times bandwidth of 1-bit code. A receiver uses same sequence to demodulate the signal. As can be seen on the figure, when you input a message to the modulator and you give a spreading generator, and the spreaded signal is then transmitted through a channel. And the receiver, on the receiving side, it has a demodulator that uses the same spreading signal to despread the signal, and then we get the output message. So what do we use to spread the signal? PN sequences come into the play, right? A pseudo-random noise sequence, that is a PN sequence or a code, is a binary sequence that exhibits randomness properties but has a finite length and is therefore deterministic. PN sequences are very easy to generate. They can be generated using linear feedback shift registers, shortly called LFSRs. PN sequences bridge the bandwidth of the modulating signal over a wide radio spectrum. They are usually used to generate the gold code sequence. Here's a gold code sequence generator. The feedback polynomials that have been chosen are 1 plus x squared plus x power 5 and 1 plus x squared plus x power 4 plus x power 5. The first polynomial corresponds to a Pn sequence Pn1 and the second polynomial corresponds to Pn sequence Pn2. Maximum length of Pn sequence is 63-bit length and is generated by XORing bit 2 and bit 3 of 6-bit random shift register LSR1. Maximum length of Pn2 sequence is again 63-bit length and is generated by XORing bit 3 and 4 of another 6-bit random shift generator register LSR2. Excuse me. So let me illustrate a spreading. Suppose the input data is 101. The goal sequence is 1001101. Each bit in the input data is XORed with all the bits in gold code, and then we get the spreaded sequence as 011001001001101 and 0110010. It is pretty obvious here. Then the input data, suppose you consider the input data 1 and you XOR the whole code sequence with the input data, so you get the complement of it. And for the second bit it is 0, the input data is 0, so you get the same figure. And then for the third bit it is again 1, so you use the complement of the goal sequence. The whole sequence is now the spreaded sequence. So the number of bits in a spreaded sequence here equals 3 times 7 bits, that equals to 21 bits. Let us now move on to the spreading illustration. So can at the receiver side all operations are reversed to get the output signal. Each set of 7 bits in the spreaded sequence is XORed with the goal code. We get similarly 1111111 0000000111111. Adding up each 7 bits we get 101, which is the input data. Next, let us have a look at the transmitter section and receiver section in detail. So here what we're doing is the message signal is first brought to the modulo 2 addition and also to the goal code is given to the as input to the modulo 2 addition where the spreading takes place, and it is then binary phase shift gate modulated, and then the whole signal is transmitted through a channel. A channel is usually open to a lot of interference, and we usually receive a noisy direct sequence spread spectrum signal. So what we do at the receiver end is the noisy direct sequence spread spectrum signal is passed through the adaptive filters which clear out the whole interference, and then they are demodulated using binary phase shift keying, and then we despread them using the gold code sequence, the same gold code sequence as we have used in the transmitter section, and then the bits are detected to give you the output signal. Now to talk a little about adaptive filters. Some signal processing applications require that the system compensate for things outside of its direct influence. Adaptive filter algorithms allow for modeling of the outside phenomena. Also, adaptive filtering can be used strictly for analysis and synthesis of a system. Adaptive filters differ from other filters such as finite impulse response and infinite impulse response, FIR and IR, in the sense that the coefficients are not determined by a set of desired specifications. The coefficients are not fixed, they are adapted. That is, with adaptive filters, the specifications are not known and they change with time. So, to construct an adaptive filter, the following selections have to be made. Which method to use to update the coefficients of the selected filter, and whether we are to use a finite impulse response or an infinite impulse response filters, that is FIR or IR filters. So here is the basic block diagram of an adaptive filter. So we give the input